Okay, so starting out, when I started writing this presentation, I thought I'd ask ChatGPT what to say in relation to vibration testing. So I asked the question, what makes vibration testing of electric vehicle batteries difficult, in less than 20 words. So this is what it came up with. So complex battery designs, non-stationary vibration, safety risks, and accurate replication of real-world conditions make EV battery vibration testing challenging. So I thought that was a pretty good attempt from ChatGPT to come up with that. So I thought I'd better build on this, or else you guys could just ask ChatGPT and come up with answers. So let's find out whether I can add to this. So this presentation doesn't cover all of the environmental simulation tests or abuse tests associated with battery testing. So we're just going to cover vibration and shock tests. So we're not going to cover the other tests which generally come along with altitude simulation, thermal testing, electrical short circuit, the impact or crush test, or overcharge and discharge test. So we're just going to cover vibration testing. So what tests should we be doing on our batteries? So I just thought I'd cover this aspect of things in relation to why you're doing your vibration shock test. Are you doing it because you're told you have to, so whether it be regulatory approval, such as the UN 38.3 tests that lots of people quote, or are you doing it because you actually want to improve reliability and durability, or mitigate against any safety litigations at may time? So you're looking to offset any warranty claims or brand image liabilities. So these are kind of different reasons, and I think it's a different mindset whether you're just doing a test because you have to or because you actually want to. So those that are not familiar with vibration testing, I just thought I'd quickly make sure people understood the basic components of a random vibration or a vibration test setup. So what we have is a shaker system and a feedback accelerometer that's sending a signal back to the vibration controller. And this controller is obviously looking at a demand signal that you're trying to achieve, and then changing its drive output to the amplifier to the shaker to try and ensure that demand is being met. So this is the closed loop vibration system. So you have an accelerometer, a shaker with its amplifier, and a control system and a PC on top of it. The one thing I would put down as the most important system component part of the system is a suitably trained vibration test engineer. Engineers that understand what they're doing, both in planning and executing tests. So that's what I consider to be the most important part of any vibration test system. Just quickly looking at vibration test systems, so looking at the shaker side of things, there are mainly two different types of shaker systems. You've got the electrodynamic shakers and the servo-hydraulic shakers. So I've got these two graphs here that I'm going to show you. This is an electrodynamic shaker capability. So you can see here on this rather complicated nomograph that you've got lines of acceleration, which are the horizontal lines, and then you've got velocity lines, which is the next line up. You can see the 1 meter per second, 2 meter per second lines, and then you've got the displacement line at lower frequencies. So generally, electrodynamic shaker systems historically were an inch displacement, and then they started going to 2 inches displacement, and you can actually get shaker systems now that do go out to 100 mil displacement. From a velocity point of view, which is the 0.2 on the graph there, that tends to be around about as a minimum about sort of 1.8 meters per second to sort of 2 meters per second. But again, there are electrodynamic shaker systems now that can come into play and up to about 3.4 meters per second on shock tests. This velocity limit is caused by the back EMF of the velocity pushing back against the voltage being applied to the coil. And 0.3 on the graph there, the horizontal line, the acceleration limit, that is the limit caused by the force limit. So your force equals mass times acceleration for the overall system that you're moving. That's what dictates the maximum acceleration line. If I just try and overlay a hydraulic system, so on a hydraulic shaker system, these are the kind of limits that you like to see. So you can see it's a lot more low frequency you have on a hydraulic system. They do have generally at least 100 mil displacement on their shaker systems, and you can see you've got the velocity line here. The velocity line is normally down to the flow rate that you can get through the the actual hydraulic system itself. So obviously that moving backwards and forwards. And then you've got the force line here on 3. But what you'll see with the hydraulic system is the limits on what you can do and how long you can keep that maximum acceleration for really starts to roll off. And you're really talking about sort of 200 hertz, the maximum frequency with a hydraulic system. So they're the two aspects. So it kind of depends on what you're trying to achieve, whether you're just trying to put low frequency energy in or high frequency energy. So generally most people are using electrodynamic shakers now, but we have seen a bit more of a move to servo hydraulic shakers and only putting in the low frequencies on the very large battery packs. Okay, so just looking at test instrumentation. So generally we're looking at accelerometers for controlling the tests. Generally we're looking at about 4 channels of vibration control as a maximum when doing a test. You generally won't want to put more than 4 channels as control, but you need to look at your control strategy, and what we mean by that is where you're putting your control accelerometers, and then are you using maximum or average control, and this really starts looking at the different inputs to your test item, your battery, to ensure your test requirements are being met. What we'd also, it's a slightly different terminology, is actually add checkpoints on there, so that there might be both in axis and out of axis checkpoints that you're checking as part of your conformity to ensure you're meeting the requirements for either cross-axis vibration or checking that you've got the right inputs to the test items. So they might not be part of the control strategy, so you might not be controlling them, but you're checking these positions to ensure that these are giving you the right vibration levels into the test item. So yeah, control positions where they're actually part of the closed loop control loop, and then you have checkpoints which may not be part of the control loop but are ones that you're trying to identify how close they're meeting the requirement. And there are requirements now whereby the variation in levels across the product should be checked as well. So not just your average control should be meeting the demand line, but how much variation between the individual channels and the inputs to your test item to ensure that they are not varying too much because you're doing too much averaging. The other side of the accelerometers is you might be doing product monitoring inside and around the actual test item itself. We've now got systems where people are trying to monitor over 180 channels and above. So these are normally validating structural and internal responses inside the battery packs themselves. So people are really starting to look more and more at what's going on inside battery packs and checking for changes in frequency response and amplitude during these endurance tests. They also help to highlight non-linear responses to changing amplitudes. So this really is a kind of an issue associated with accelerated endurance tests where you're time compressing your endurance tests. If you're starting to get changes in response at the endurance test level, then you might need to rethink the actual test levels you're applying, as you may get non-realistic failures because of it. Normally, these internal accelerometers inside battery packs, there's obviously not a lot of space inside battery packs, so you are looking to get in some of the really small Tigany ultra miniature accelerometers to do this. So here's some examples of some really quite small accelerometers you can get now. I think the smallest is about 6 millimeter cubed, about 0.8 of a gram as a triaxial accelerometer. Other sensors that are commonly being used in doing battery pack vibration, getting asked to do strain gauges. People like to sort of validate their models, and they like to have strain data. So on the VR front, we're kind of suggesting that you use remote strain gauge amplifiers, so these kind of devices here, and then you've buffered the signal, and then obviously you can send that signal as a voltage input to the vibration controller. So rather than having to have separate strain inputs on the vibration controller, use these remote strain gauge amplifiers, or you can use normal conventional strain gauge amplifiers instead. But these tiny little devices obviously help you buffer the signal and get rid of noise at that source as locally to the strain gauge as possible. So this is a nice simple solution for using strain gauges with a vibration test. The other aspect of instrumentation, people using temperature sensors inside the battery pack, obviously for safety reasons and looking at the charge discharge cycles or whatever and seeing what temperatures are being generated. And this can also be fed back into the vibration controller and used as a trip to stop vibration if excessive heat is seen within the battery pack. So on the 9500 and 10500 controllers, you've got those inputs available on the back of the controllers that log at 1 hertz. So you can take these temperature measurements and actually use them and report them in your reports, as well as use them as safety trips. Other aspects of instrumentation that's being looked at and used is pressure sensors. So pressure mapping sensors, like you see on the screen there, to looking at the swelling and pressure build up within battery packs. And one thing I've not seen as much, but I've put it down, is force sensors. So looking at force inputs, because some of the big battery packs, they react so much with their local surroundings, and the responses are going to be affected by the fixturing. So if your fixture's too stiff compared to the real life way in a stiffening up structure, you may get different responses. So quite often you can break things by putting in too much force. So you have these force sensors that they're quite often used in satellite testing. So you can actually use these. Here, this is an example of satellite testing, whereby you've got a ring of force sensors and you can force limit the vibration to try and stop some of the low frequency modes from being overexcited. So you can limit the vibration in relation to force. Here's a quick overview just for those that obviously not familiar with vibration testing. The main aspects, we have sine vibration testing, so that'll be fixed frequency or swept sine vibration. There's also sine resonant track Durell. So some of the specifications not on the battery testing, as I'm aware. You've got resonant track dwell, so you actually lock onto a resonance and then keep it on the maximum amplitude response, and then track the actual resonance if it changes during the actual testing. And then another one is sine and sine testing, so putting multiple sine tones on at the same time. Random vibrations, you've got the normal standard broadband random at the top, and then you've got variants of that which are random on random, where you may have moving high amplitude narrow bands that move as speeds change. And then you've got sine on random testing, which is another variant but uses sine tones instead of narrow bands. So slightly different there in relation to their fixed amplitude, or they're not varying like a narrow band would be in a random way. You've got the Catosian control there as well. So if you know that your vibration environment is non-Gaussian, then you've got the Catosian control, and then you've got the sine on random and random if you want to do a combination of the two. On the shock side of things, you've got that classical shock, which is either half sine or terminal peak or trapezoidal square wave type pulses. So these are kind of simplified classical shock pulses. Or you can do a user-defined transient. So if you've got known shapes of pulses, you can do user-defined transient, so we can control complex shocks rather than having to rely on a simple classical waveform. And then something I would always push people to do is to measure the shock response spectrum whenever they're doing shocks on shakers, just so you can see what effect the compensation pulses have, where you need to start and stop at zero velocity and in the middle travel of displacement. So these can affect the low frequency input to your shock and give you a different shock response. Shock response spectrum can also be used as a synthesis method, so you can come up with a complex waveform that meets the shock response spectrum. And then on the end there, we've got the field data replication, which is long time history replication, and transient capture. So if you're doing drop shock tests or drops on that, you can capture the response of the product. Okay, so just having a look at what tests you should be doing and when you should be testing. It really comes down at the moment in relation to how complex a test you want to do. So we've got obviously overall battery pack assemblies, but we've got within them, we've got the cells. So what tests should be done at the cell level, at the module level, looking at cell interactions. So this is a module here within a battery pack. You've obviously got the battery management system, the coolant system, the crash protection structure itself, and then obviously interconnecting cables and hoses. So really trying to decide at what level you want to test the components of your battery pack, or whether you only want to test it at the full level battery pack. Kind of comes down to how complex a test you want to make, and also how realistic you can actually make the testing of the test article. So when I say the compromise here, there's a testing compromise in relation to your ability to apply the correct vibration amplitudes and frequencies. So it's easier on a small item to get the correct vibration levels into a small item than trying to replicate the vibration levels across a whole huge structure that's going to have very low frequency modes, and the test fixtures going to have very come into play in relation to the mounting of the battery pack onto it to go into the top level. So testing a cell, you should be able to get the correct vibration amplitudes and frequencies. The other compromise is the ability to physically replicate the mechanical interfaces. So if you have a solid fixture and you mount a test cell into it, you're going to be able to get the exact vibration amplitudes and frequencies, but does that physically replicate the mechanical interface when it's inside the battery module and the battery pack itself? So these are the kind of compromises that you're going to get. So looking at the different levels of testing. I just thought I'd give you a quick detour into non-linearities at this stage. So what are non-linearities and why they're so important? So non-linearities are simply when vibration responses of a product or a structure changes in amplitude and frequency when you change the input levels. So this is things like rattling and impact noise that goes on are typically non-linear events, but you can get other non-linear events because of rubber systems hardening up the more you actually squeeze them and they go solid. So you quite often just by increasing the vibration level, the structure becomes more non-linear. But rattles and impacts are definitely a non-linear event whereby you get to a certain amplitude and then things start hitting where at the lower levels they don't. So, and this can obviously create lots of high frequency energy that you haven't put into the system, or can cause problems in controlling a test because you're now no longer putting in any energy at high frequencies because the system is generating all these high frequencies. So the main thing here is you should always check your product's response to the vibration input at lower levels and see when you get significant changes in this response. So this is why you should be monitoring what's going on inside your product. I would also say that non-linearities are the enemy of accelerated tests. All of the algorithms associated with accelerating tests all assume linearity when you increase the level. So the fatigue damage spectrum all assume that you've got linear kind of material properties and that non-linearities are not occurring. So really, you should be looking on sign tests, checking for non-linearities, checking total harmonic distortion measurement signal tolerances, and comparing your low-level track and filter responses with the higher durability test responses. So the number one rule is don't over-accelerate your test beyond the operational levels, or if you do, you should check, you should decelerate the test levels to where non-linearities are removed. So, and don't ever live with rattles and impact noise on your product. Always find out what the cause is and try and remedy it, because they're only going to cause problems in service if you've got rattles and impacts. Okay, so cell testing level. So here's a few examples of cell vibration test fixtures. Generally, cell level vibration is either done for transport reasons, for transport clearance of packaged cells going out for transport, or looking at electrical performance and physical property changes within a battery. And obviously unscheduled energetic releases of energy, fires and explosions. I'm not a fan of clamping a cell in these kind of fixtures or whatever, because you may as well encase it in lead and shake it and obviously try and get energy into them. It's not really replicating how the cell is mounted when it's inside a battery pack, unless you're physically encasing it in exactly the same way it is in a battery pack. I would prefer people to be doing kind of cell level vibrations with the bond wires on in a more representative way. So more either a sub module level to try and get an idea of what's going on within the cells and how they're reacting with each other. So that, but generally these cell level vibration tests are all done on a vertical shaker, and you can kind of rotate the product around using a kind of cube fixture like this, so you can do all three axes on a vertical shaker. Here's some examples of insides of damage to cells. This is from an 18650 cylindrical lithium-ion cell after 300 shocks. You can see the original undamaged tissue to the new kind of damage situation. So damage does happen to inside cells, as well as obviously interaction between the cell and the local environment around it. So this is obviously quite a bit of damage. And this is another view of some separated layers on some batteries where there's been cracking between the separated layers. So yeah, cells do get damaged by vibration. So just seeing what's involved with doing small-scale cell vibration tests. So to do small-scale vibration tests, you're looking at a fairly small shaker. You can probably get away with a permanent magnet shaker up to say 450 newtons. So not particularly big or expensive, or you could go to the sort of 2-3 kilonewton DC field coil type of electrodynamic shaker. So there's a bit of a gap there between the size of the permanent magnet electrodynamic shakers and the DC field coil ones, and there's a huge difference in size between a 450 newton shaker permanent magnet and the size of a DC field coil electrodynamic shaker. Generally, you're only looking at a 2 to 4 channel controller for doing these kind of cell vibration tests, and whatever software modules you need for the type of testing you're doing. You've seen simple fixturing can be quite simple, but it's not always easy to replicate the module interface and particularly the bond wires and stuff like that when you're doing cell level vibration tests. There obviously are package cell level vibration tests for the UN 38.3 to get transport clearance for shipping cells around doing that, but that doesn't really require a lot of fixturing. So, and generally these fixtures, as you've seen before, whatever, you rotate them around, and you don't really need to do cell vibration in relation to gravity, so you can rotate the product in relation to gravity. Generally, you'd be using generic test standards at the moment. SWEP sign tests, but think about the test frequencies you're going to do. It might be a case of don't waste time testing at frequencies below the first natural frequency of the cell or the cell within its fixture. So always look at the minimum maximum frequencies there, because there's no point in testing a cell to 10 hertz. It's just not going to react to it. So you could probably save yourself some time there by truncating the lowest frequencies. Obviously, device monitoring, you'll be looking at electrical performance, charge and discharge cycles, and what physical parameters you might want to check before and after the cell, or do pre and post x-rays. I think there's even some looking at doing high-speed x-ray imaging during vibration to see if you can see what's going on inside during vibration. But, that's probably more of a very specialist task. From a vibration and competency side of things, you just really need basic knowledge of vibration testing to do cell level vibration testing. From a safety side of things, just standard risk assessments, carry out a fire risk assessment. Obviously, will the testing be done unattended or attended? Is somebody always going to be there while the vibration is happening? What sort of shutdown systems you're going to put in place, or any fire suppression systems? So I'll cover that later on in the presentation. And obviously include fume extraction. So just moving on to what kind of full-scale module or battery pack testing. So the shaker size here, it could be looking at anything from a 22 kilonewton shaker up to, there are 300 kilonewton shakers out there for doing the huge vibration battery packs, or you could be looking at servo hydraulic systems, because the vibration could be just the low frequency when you're doing the whole battery pack is all you're interested in, if you may have covered the higher frequency at a lower module level. Again, I know we covered this earlier, but the control systems, you could be looking at anywhere from a 16 to a 200 channel controller, and the software modules you need to run your different types. Slip tables, you could get away easily with a 750 millimeter square slip table, but there are 2 meter square slip tables out there in all sorts of different configurations, and abilities to reconfigure them with outrigger bearings and all sorts of things like this, where people are trying to reduce the weight of the slip tables and but still have it guided. And you've got the same issue with head expanders. You've got the compromise there with it's almost impossible to develop a head expander that's 2 meters square or oblong. And it's always going to be a compromise on mass and stiffness and natural frequencies and the damping on these head expanders. They're always going to have mode shapes within the realms of the battery pack's own responses as well. So this is where it all becomes very difficult for doing battery pack testing. Fixtures, yeah, where do you start in relation to realism while ensuring the test is possible? Obviously, you notice a lot of the fixtures that I'll show you in a minute all kind of have the interface with the battery all around its edge, which is all where that you're getting the highest variation in amplitude with the vibration head expander with its mode shapes. So fixturing is a real issue in relation to how to hold these big battery packs. Test amplitudes and frequencies, there's more of a move to be doing test tailoring at this level rather than standard regulatory tests, basically because yeah, at this level standard regulatory tests aren't really relevant when you've got the kind of whole response of the vehicle and the design of the battery pack are actually driving what vibration is occurring within the car itself. The battery pack's such a structural element of the actual car that having standard regulatory input that covers everybody, you're either going to over test or under test depending on the actual battery pack itself. So, you'll need to obviously look at control strategies and where to control from, and also look at what your minimum and maximum frequency should be. Again, the same again, you're looking at electrical performance during testing, having looked at what your pass-fail criteria are, looking at physical parameters, what you're going to check before and afterwards, as well as are you going to X-ray. Getting battery packs apart is not always easy, so yeah, so whether you're going to go down the X-ray route to work out what's going on inside. Obviously, training competency, doing big battery pack, you've got to really increase your knowledge and experience on vibration testing and actually understand the physical things that are going on in relation to your test facility, and know your test facility in a lot more detail than you would with a little cell-based vibration test. Yeah, the whole kind of interaction between the test facility and the battery pack really starts coming into play, and looking at how you're going to control the test. Looking at cross-axis, am I damaging the shaker systems? People are looking at multi and dual shaker systems for doing this, and you can do a lot of damage if you don't know what you're doing with multi-shaker tests and how they're controlled. Obviously, from a safety and productivity side of things, this starts getting a little bit more risky with a big fire potential, so really need to have a look at how you're going to mitigate in relation to a battery catching on fire during a testing. I come from an explosive background, and we always test things in a separate building away from everybody else, and looking at the kind of aftermath of a big battery fire and how long it's going to burn for is something that really should be looked at. Here's a quick look at some of the facilities that are around at the moment. Here's I think it's a 200 kilonewton system here, with a head expander and a slip table to one side. Generally, the battery packs are being done at temperature as well, or they're combining temperature and vibration within the same facility. So this is where we're kind of looking at mode shapes are going to affect things and multi-point control. So yeah, please look at the variation between your control points. Don't just look at the average control trace. Have a look at what the different control positions are giving you. So there are multi-shaker configurations with twin shaker systems that are trying to reduce the size of any head expanders. So you've got 2 inputs rather than 1. So that certainly might be something to look at. Here's an example of a very large head expander. You can see the person at the back there. So you can get an idea of scale of how big these vibration test facilities are. This is a big head expander, and then this plate's put on the top here. And then there are 4 locations in the corner where you've got guidance bearings as well to try and protect the shaker underneath from any lateral and mode shape problems that are going to occur. So you can see these bearings on this next picture. Okay, so just making sure that you're understanding when you've got head expanders, these are what I mean by the mode shapes that are occurring. So these are the different modes that head expanders are going to go into. So you get more and more complex mode shapes as you increase frequencies. But you can see generally you're always going to get the higher amplitudes around the peripheral of the head expander. The center at certain frequencies won't move at all while the edge is flapping away. So depending on what frequencies and the mode shapes that you're tending. So here's a vibration fixture from on a large battery pack here. So just kind of show you the different kind of measurement points and checkpoints that might be on there with different control. Where we're looking at the variation and how to control this fixture and the different variations in acceleration levels. So if you don't do this mapping process properly and you start controlling in the wrong areas, you're really going to start over testing or under testing. So there's been a lot that you can simply get completely different results by controlling in the wrong position. So you really need to understand all the interfaces and how they're varying with altitude across the frequency range. We'll just go through. Here's a multi-shaker test facility. It might be the future and help out with doing battery packs, doing 3-axis of testing with multi-shaker systems. So this is actually a rail test facility, but I just thought I'd put it up as a possible future look at doing vibration testing on battery packs. Here's a quick look at test standards associated with lithium-ion battery packs. So you've got the United Nations, the UN 33.8 United Nations standard. So this is a transport of dangerous goods. So this level of vibration and shock testing that's within that specification should really be aimed at anything that's being packaged and transported around. So that is for regulatory approval of transportation of lithium-ion batteries. So you should be doing that test on the actual transportation packages. But I've seen it being used and banded around as a possible test to be applied to a battery pack itself. But I'd always be looking for that to be done in whichever way the battery pack is going to be transported. You've got the IEC level ones here, the 62660, and the ISO standard for testing road vehicles. You've got the SAE standards. So the main one there is the J2380. The latest version of that was upgraded in 2021-12. There's BATSO standard here. So this is a cooperative between TUV and Extra Energy and the ITRA in Taiwan and the UL laboratories. So that's the BATSO standard, and there's the ANSI, the UL standards here as well. So I'll just leave them up on the screen for a little bit in case you redo the webinar, and you can write those down. I'm just going to put these ones up here. This is the IEC or the ISO standards associated with the different forms of vibration that you might be applying to a battery. So these are what I would call the control standards. So this tells you how to go about doing a vibration test and the limits and tolerances that should be applied. Quite often these standards don't really go into the full details of how you should be doing a vibration test and how you should be controlling it. So these ones here really should be your guiding test methods on how you should be carrying out a vibration or a shock test. Okay? So this is the kind of the gold standard methods that you should be using, and using the standards from the amplitudes and levels. So yeah, the UN 38.3 dangerous goods set of safe to transport regulations really should be applied to the transport package configuration and not directly to the test item. As of the January 2020, all shipments of lithium-ion batteries must provide a test summary that proves the products have passed the UN 38.3. So the actual shipment themselves have to contain proof that the shipments have passed that vibration standard. So this kind of comes into question when you're doing 38.3 Should you be able to self-certify, or do you need to use an independent third test laboratory? Using a third-party laboratory helps with mitigation and liability should an incident occur. If you're using a third-party test laboratory, it's best if the test lab is accredited to 17025 and approved for OSHA testing as well. Whichever option you choose, all levels must be tested. If you're being transported, then the cell needs to be, if that's being transported, needs to be regulatory approved, as well as battery modules if you're transporting battery modules and battery packs themselves. So at cell level, these are the kind of standards there for cell level testing. One question I just thought I'd put up there is whether you should be doing batch testing on the cells to ensure that all cells have been kind of made to the correct standard, and there's no kind of batch processing issues within a cell. So and you also might, even though you're having your cells tested by your battery manufacturer, you still might want to do your own kind of cell level vibration test, simulating how the cell is actually held within your modules. So you can do that. Oh, and the other thing there at the bottom is in relation to, if you are doing having cell vibration tests done to a standard or whatever, it might also be useful to compare the tests that the cells are being done with the actual field environment. So you might like to use fatigue damage spectrum for that. One thing I just want to bring up on the latest J2380 is the quote from SAE on this standard now: it's preferable for a specific vibration durability profile should be developed based on actual vibration measurements for the specific electric vehicle application. So the SAE now are pulling away from standard vibration test levels and preferably asking you to come up with your own vehicle durability profile rather than relying on the standard itself to give you the vibration levels. My colleague next month, Tom, will be running through how to generate battery test profiles using field data and user information to actually come up with your own vibration test profile. So that should a nice link in with this presentation. So creating your own tests, these are the kind of things that we should be looking at. You've either got field data replication, we've got a random import software module using fatigue damage. So you can take multiple different waveforms and combine them into a single test profile based on different percentages of life from each waveform. For shocks, you've got the shock response spectrum, so we can take the envelope of lots of different shocks and then reproduce a shock based on a typical shock time waveform, which is good. And then you've got the user-defined transients for single shocks rather than a combination of shocks. And you also might like to consider our STAG software. So if you've got non-stationary environments where you've got frequencies changing with time at different speeds or whatever, it might be worth taking a look at our STAG software in order to generate signal random tests. So the whole issue with generating your own vibration profile is down to time compression of tests. You're all going to want to have time compressed tests. So this is where we kind of look at the being able to kind of accelerate tests. So if we look at the variation in stress levels of the actual environment out there, you've got a distribution of that. You've got a distribution of strength of the product over here on the right hand side, and the failure proportion is where those two interface there. So so we're looking at that. So that's the kind of proportion of that you might get failures. So obviously you can mitigate that by strengthening the product and moving it away so you don't get that overlap. But what we're doing when we accelerate a test is basically taking all these different stress levels and combining them into a single stress level that's the summation of all of those stresses into one. So ideally you'd come up with a test here, and your product is stronger over here on the right hand side. Where it becomes a problem is where you kind of can over accelerate tests and you end up with non-linear problems, and you kind of end up still causing yourself problems. Here's a quick overview of the process of fatigue damage spectrum. So we run the different waveforms through these narrowband filters. then we get a waveform from each of those filters, and then we do a rain flow counting exercise on that to look at all the different stress reversals and their amplitudes and the number of peaks at each stress reversal amplitude. We apply the material properties, the SN curve for materials, and then we sum all those up and come up with a fatigue damage spectrum associated with each of these points being plotted on the page. So that's how we accelerate tests, basically. So we're doing that. But you do need to have a quick look of ensuring that is fatigue damage spectrum the right tool for you, and whether your moving environments changing with frequencies or whatever actually comes up with a better test. So that's something to just have a look at, see whether STAG would actually give you a better test. So the issue with test tailoring is obviously this issue in relation to making sure that you don't get a false pass or a false fail in relation to, you guys might measure environments, but you don't know what percentage of life, whatever customers spend doing different speeds or different levels, or how big the potholes are going to be in all the different areas of the world. So this is the kind of issue associated with test tailoring and your confidence in your test level. So we always want to get a true pass. We also want to ensure that we get our true fails, so failing a defective product or whatever. But what we don't want to have is either a false pass or a false fail where we've damaged good product. So this is the quandary with our testing. So yeah, no testing is the equivalent of bad testing is the equivalent of no testing. So yeah, the bottom line really on test profiling is it can be preferred if sufficient product maturity or segregation in data is available, answers questions about the relevance of tests in relation to product usage, environment, and failure modes. It can lead to more robust or optimized designs over time. Custom profiles upfront warranties, reduces warranty, speeds up validation though running changes to design. So I'm a very advocate for tailored testing rather than standard specifications, but there is a kind of plus and minuses associated. Here's a quick look at our ObserView software in relation to some measurements on a real battery pack on a car and the kind of things that we can do nowadays within the software. So I just thought I'd quickly pop that up just to show you what that process looks like in the graphs that are generated during the validation process of creating your own test profile. And then this is something else that can be used for the fatigue damage software, is a comparative tool to have a look at your test profiles compared to your real measurements that you've made inside the car. So you can have a look to see, compare the fatigue damage of the tests that you've run and the responses inside the battery pack with the same response in the field, and just see how much life the test is actually giving you before you might get to a failure. So fatigue damage also has that lovely capability. So you can see on the graph here, you can put the limits where it'll highlight at what frequencies the real environment might be above the test environment you've done. Okay, I just thought I'd cover shock testing now, just to ensure that you're doing. This is just a 1 meter drop, so a typical kind of safety drop of what might happen on a battery pack, instrumented up with accelerometers inside and it landing. My one thing here, I've done a lot of drop tests on explosives, and it's very difficult to get clean drops. And obviously you'll see from the from this one here, this particular drop did not land flat as you might expect, so all of the damage was in that corner there. So it's very easy to get very different results from what you think is the same test. We always used to run our drop tests on explosives from down zip wires and stuff to ensure that at the point of interface with the ground, it was exactly in the orientation that we wanted it to be. So we had like a cradle above it with to ensure that it held its orientation until it hit the ground. So we could predetermine exactly what angle we wanted it to hit the ground at. So that might be something that people should look at when doing battery drop tests. Because obviously if you hit a corner or if it hits you're going to get local deformation, but if you get a true flat drop on the base of the battery pack, the shock is far greater because there's less deformation there. So you've not got that crumple zone to reduce the drop level, the shock level. Shocks on shakers. This is a bit of a campaign of mine in relation to people looking at the effects of these compensation pulses on either side of the shock pulse here. So you've got the main shock pulse there, but we have these compensation pulses either side to ensure that we start and stop with a zero velocity and the midpoint displacement there. This is the shock response spectrum. So this thin line here in the middle is the actual shock response spectrum from a proper half sine shock. Here are all of the different actual SRSs due to the different compensation pulses. So you can see here that the compensation pulses quite often give you an under test at low frequencies, but then they'll give you a huge over test at these kind of mid regions here after that initial kind of velocity line on the shock response spectrum. So if your product was to respond in areas where you have these peaks, you could be massively over testing your test item if it responds where you've got these high amplitude increases because of your compensation pulse. So it's something that anybody doing shock testing on shakers, always look at your shock response spectrum and ensure that the natural frequency of your product isn't in any of these areas where you're over testing or under testing because of your compensation pulses. So the rule of thumb now from my side of things is have the smallest compensation pulses that you can get away with to ensure that you're not distorting the shock response spectrum associated with your half sine shock. So yeah, that's my campaign on shock tests on shakers and shock response spectrum. Okay, fire and safety risks next. So we're busy running out of time, but hopefully we've just got enough time. Laboratory design, looking at battery safety, physically isolate the test layer, put it in a separate test cell or a test building, monitor and detect, so automated responses in detecting fires and safety risks associated with that. You've got fire suppression, inert gas, water mist, sand or complete water deluge systems. Also consider obviously fume extraction. There's a lot of fumes associated with the lithium battery fires, so make sure you've got an automated or a manual response system for switching on that fume extraction. And then the other thing is ensure you've got video surveillance so you can see what's going on. I'm sure most people know that deal with batteries or whatever, that you can get thermal runaway within lithium-ion battery packs or whatever. And when the cathode breaks down, it generates its own oxygen. So it's not something that's going to go out by itself or whatever, unless you reduce the heat associated with the breakdown of the cathode. Otherwise, it's just going to keep burning away. So that's the kind of main issue of why you get to thermal runaway with lithium-ion battery packs. Here's a sand hopper system for a simple test rig. So you've got these emergency stop buttons, and then you've got a sand hopper above the shaker system here. So it's going to dump that sand on top of the there if the temperature exceeds 60 degrees C. So you've got an automated response and then obviously a manual emergency stop as well. So that the shaker's in the space below here. So that's for a typical safety rig for a cell vibration test facility. Here's a water deluge system from one of the shaker manufacturers. That this chamber comes down, seals itself on top of the shaker head, and then deluges water inside that chamber, completely immerses it in water. So it ends up like this. So it basically shuts down the shaker system, drops it to its bottom height, comes down, seals on top of it, and completely deluges it with water. Not sure exactly what happens when you short everything out like this, whatever, but this is certainly a system that's known to work. Okay, hopefully you've all managed to hear me right to the end of the system, but just thought I would cover our comprehensive support. Customer support is key to us or whatever. Have a look at our educated training programs as well. So if you've got any questions, please contact us at Vibration Research via sales and support. Hopefully you've enjoyed listening to me rabbit on about battery vibration test. But please get in contact if you've got any questions.